Okay, so from the first part of the quiz, it seems we need to. I will tell you how to do it. I don't have time to really go over it in detail. There are three main ways that you can do this. One is an inverter on the enable and then OR gates on the outputs. The other is if you bubble push that through the OR gates, you just turn them into NAND gates with the outputs and the enable. But what I was hoping that you would see is on question 2, the second process, it's if else, tells you it's selecting. That tells you it should make a mux. So there are multiple ways that you can go about it, but those are the main three that I can think of.
So for the second individual X bit input bit.
The second one is just connecting the Y internal to the Y external, or it's just driving the Y external to one. The first process block is the one that was
Right.
doing the priority encoder.
Okay.
All right. So we are going to be building upon these things, so do review combinational logic blocks and like connecting them, things like that. All right, but I am going to prepare you now for the lab today. So it's the VHDL implementation of latches and flip-flops. And for the most part, a lot of the code is provided for us. And there's just a few changes that I'm going to make sure that you guys have everything you need. So here, when you make the entity for this SR latch, these are inputs, these are outputs, right? But as you know from previous labs, if I am trying to read from an output, what does VHDL say? Can't do that. So the code provided by the lab is a little bit wrong, so let's fix it. So we just make these internal. So you'll have to also add the internal declarations, right? And then because they are internal, we would then be able to read from them, right? But now we need to still make sure that our output is connected. So we just connect the outputs to the internal bits. Okay. So Q bar like that. So now we can read from what we want as outputs without VHDL complaining. But remember, you need to declare signals as internals. You need to declare them, right? So standard logic Q underscore I. Yeah.
On the quiz, wasn't the enable supposed to be a signal in the code?
In the code, enable, it is input, standard logic. It's fine. I don't see a error there. All right. So the other thing is it also provides this implementation. This implementation is not synthesizable onto the board. Don't do that one. All right, so the next thing that you will make is what we built upon with the SR latch. This is the SR latch with an enable, right? So for this one, we just have to add a few more signals, right? So we're going to create RE, standard logic, and let's also make SE, standard logic, and let's also define what we're going to use as Q internal. Again, standard logic, Q bar internal, standard logic. So this is RE, this is SE, this is Q in, this is Q bar in, right? So then after we have now the begin, then we can do our data flow equations, right? So RE needs to be what? RE here. R and E, right? SE, what does it need to be?
Yes.
S and E. And then we need to make Q underscore, we need to make Q internal. So Q internal is what? Q bar what? Internal. Q bar internal. And then the last bit is Q internal, not Q internal, but Q becomes Q internal. And Q bar, not internal, becomes Q bar internal. Right? And then that's it for this. You make a test bench, test all of these cases, and then you're done. And the next thing that we made was the D latch, right? Yes. If you have two zeros. So you're going to, when you make your test bench, define some initial values for the inputs. You can just have your first test be reset to make sure that it is 0. And then your second test can be maybe the 0, 0 case. And then in that case, it should just output the previous one, which was 0. If you start with the 0, 0 case, it will still just output 0 because of the AND gates with the enable. So it'll be forced to, no, it might still just show as undefined. So just don't start with 0, 0. And, but even then you can start with 0, 0 and make sure that it still stays undefined. Things like that.
But you should just test all of these cases because there are only a few cases, right? Question.
When test bench, how do we output latch?
You'll just, what it means by latch is the output doesn't change. It keeps the previous value. So whatever the previous test was, it doesn't change. So you should look at the waveform, and if it's 1 and the next test, you make sure that it stays 1. That's it. Any other question? Okay. So the delatch. For the delatch, we're doing this in a behavioral design. So this is where we're breaking our convention of using behavioral process blocks to be purely combinational. Because remember, we had those rules that we were following to make sure that it was purely combinational. And the rule that we're breaking here is we don't have every condition defined, right? So this is how we create latches, because if the condition is not in the if-else block, that means it just keeps the previous value. So that's where we're latching. And the key thing here is in this sensitivity list, we have D and we have enable. Because when enable is 1, if D changes, where our latch is supposed to be transparent, right? So the outputs to Q and Q bar should change. It's not only determined by when enable switches. So we need both of these in the sensitivity list. And then the if statement is just, if it is enabled, we're going to update the Q based on D. If it's not, that's where we're holding the previous value. So that's what I meant every time I was talking about these process blocks, that it would create a latch if you did not define your default case. So there's no default case here, there's no else. So that's why it's going to just hold on to the previous value. And that's how it's going to get this latch behavior.
Do we need to do anything on the board if it's all going to be test bench?
It'll still ask you to like put switches as D, and you'll have one of the switches as your enable. So you can still test these things.
So
All right, so this is the part that I wanted to cover a little bit more to make sure that you understood what each of these things were. So the first flip-flop that you're making is just a normal flip-flop, no enable, right? So that means at rising edge, so whenever the clock changes, and then we're only checking if it's rising edge clock, then we update Q to what the input D currently is. And then it's not until the next rising edge that we update. So that's why you can just implement it with this simple process if statement.
do we have to define rising edge, or is that like a method in the?
This is rising edge is a keyword.
Okay.
And falling edge is also a keyword. But the lab is not asking you to use falling edge. Typically, rising edge is the convention that's used. So what I wanted to clarify is this with a reset or a clear, they're basically the same thing. But this one is synchronous, this one is asynchronous. So what we mean by synchronous is if here this is our clock. So we have this square wave. And then we have on the input D, and then we have reset. I'm just going to put it as R, and then Q. So if we have, and I'm going to call this Q S, and then let's see, can I move this? It won't erase. I'm just going to erase this. I want D R Q synchronous, Q asynchronous. So let's just say that we set D to be 1 pause edge, right? And then next pause edge, let's also keep it 1. And let's just keep D as 1. But our resets or clear, so let's just, clear is the same thing as reset, it's just called something else. Here, let's say that we want to reset it here. If we look at Q, at the outputs, this is where we're going to see the difference. So initially it's 0, and then at the pause edge, it samples D and it becomes 1, right? And then for the synchronous one, it's not until the pause edge that we see we would sample D, but the reset is 1. And as you can see, reset is checked first, right? So it's the higher priority. So because of that, this would change to 0. And then at the next positive edge, it would change back to 1. With the asynchronous resets, we again, when reset is 0, D is 1, pause edge, we become 1. But we don't wait for the pause edge for asynchronous. It's asynchronous because we can reset at any time. So it becomes 0. And then it doesn't become 1 again until the next pause edge and reset is 0. So you see how it becomes 0 earlier. It doesn't wait for the pause edge. Because with the asynchronous, we check clear and then we check rising edge. But with the synchronous, rising edge is first, and then within we check reset first. And only if reset is 0 do we update the value of the flip-flop. So you should see this difference in the waveforms between your test bench for the flip-flop with a synchronous resets and asynchronous resets.
So that was an earlier shift because it activates earlier.
Yeah, because it doesn't wait for the pause edge. So whenever the reset changes, and in this case it's called clear, and that's also why it's in the sensitivity list. It doesn't matter if it's rising edge or not. As soon as clear signal is sent, it drives it to 0. So you'll be making these 3 flip-flops. Any questions on the difference between those? It's the main thing that's usually confusing for students. All right, so we have 4 minutes. Did you want to see this drawn or something? Okay.
Can you show the buttons?
Yeah. So I'm just going to draw it over here, though. So let's see. We have our box. We have the encoder. 2, 3. This is X0, X1, X2. We wanted to add the enable. This is y0, y1. So we can do it with these muxes. So 0, 1, 0, 1. So what was it if the enable is okay, so this is 1, this is 1, 0 is y0, 0 is y. And this is y0, this is y1. So that's what it would look like with muxes.
I don't see any.
Yeah.
Two outputs.
You could, if you specified like, if you drew, say this is y1, y0, if you combine them into one wire and then you said that they were two and then you use one mux, it would be fine. Yeah.
What about the example? Yeah.
So the OR gates and the inverter would be you invert. So this is enable, invert enable, and then you OR gates with this y0, and you OR gates with this y1. Because now if enable is 0, it becomes a 1, and then it just becomes y0 or y1. But if enable is 1, it forces the, if it's 1, we invert it, it becomes 0. So it becomes 0 out here. So then you just need to add inverters.
It doesn't just become y0, y1.
No, because if enable is 1, it becomes 0 here. Oh wait, no.
Something or 0 is just that something, right?
Yeah. So when enable is 0, it becomes 1, and it forces it to 1. Which is what we want. Yeah, and then when it's 1, it becomes y0, y1. And then the NAND gate is just if I bubble push this through, these OR gates become NAND gates. And I just don't invert. So it's the same thing. Make sense? Okay, so do review that. It will be helpful to be able to know these combinational blocks for the future. We will be drawing many diagrams like this.
When we do the SR latches and flip flops, when we'll be able to generate the schematic that we're doing behavior, right?
So you'll generate the schematic?
Yeah.
Yeah, sure.
Just to know that it looks like an SR latch or what it is.
Yeah.
The way you described it actually was pretty close to what I did, other than the, I think I just did maybe the inputs a little different way with.
Can you tell them the poll code?
Put 2 lines in instead
The
of.
poll, we didn't do the poll, it's 952, 952. 952.
Right now.
Yeah, I'll keep it open.